Okay, let's take a look at the mass spectroscopy POGIL. So it says, how do we know isotopes exist? So you can see, this is going to show you like the inner workings of a mass spectrometer. So before we start that, let's take a look at the why. So it says, when John Dalton proposed the first formal atomic theory, he stated that atoms of the same element are identical, which we know now that is not true anymore, because today we know it's not true. Many elements contain several different isotopes or atoms at different mass. So I'm going to be using highlighter on this a lot. So if you have a highlighter, go ahead and get it out, because that's the main idea, obviously, behind an isotope is that they have a different mass. Mass spectroscopy is the principal technique used to study isotopes. It is used to both count and weigh atoms in a sample, not just in the traditional sense. So there are four different things happening, as it says here, and according to Model 1, what four processes occur inside a mass spectrometer. So if we look at the picture, we can tell that one of the processes is ionization, and then we have acceleration, and then we have deflection, and then we have detection. So those are the four processes. If you don't want to have to write that there, you can just highlight those, that's fine. And you can like write number 1, C highlighting or whatever. Okay, consider where the sample is introduced into the mass spectrometer in Model 1. Which of the four processes from question 1 is the first process? So just take a look at it. What does it look like happens first? If we're starting with the particles here and they're coming through this way, the first thing obviously is ionization. It's the first thing we come to. So that's what number 2 is. Take a look and read through number 3 and see if you can come up with what these are, and pause the video, and then see if you have the same things I put. Okay, let me switch because I got to switch to my pen here. All right, I'm switching my pen. So the first one says, ions collide with a metal plate. Electrons are transferred from the metal to the ion, producing a current, thus a signal to the computer. Because it's signaling to the computer, that's indicating it's a detection. So I'm putting that there. Ions are attracted to the negative side of an electromagnetic field, causing separation of the mixture based on mass and charge. You can see here in the picture down here that we have a separation of charges, and so that's happening at the deflection. Electrons are knocked off sample particles to form mostly positive ions. So we look at the picture, and mostly positive ions is where we're going to have what? Well, if you look up here at the very beginning here, this is mostly positive because here's the positive ion here. So that's going to be at, well, it's before this actual steps. It's before that. So we're going to say that's ionization. And then ions move towards a series of charged plates to form a narrow beam of high-speed particles. And again, we're talking about the high speed. And here's the plates, right? So that makes sense. That's acceleration. Okay. All right, so let's take a look at the next thing. When a sample is injected into the mass spectrometer, do the atoms or molecules turn into positive or negative ions? So take a look at the picture. So when the molecules turn into, when they're injected into the mass spectrometer. So if you look at the picture, it's a metal, right? And metals typically do what? They become positive. So I'm going to put, it's Mg plus 2. And it says justify with at least 2 pieces of evidence. So it shows Mg plus 2 there. And also it shows that particles are attracted. Let's see. Where does it have it attracted? It has it attracted to it should have it attracted to the negative in the picture. Positive because they're metals. And that's actually good enough. Positive because they're metals, and also in this area here, it shows it as positive. Okay, I'm not going to write all that. According to Model 1, what causes the sample mixture to become separated? So the sample is separated here. Here's a separation, right? And the sample is separated based on mass differences, which we should have seen. Well, it just talks about up here weighing and counting, but they're separated based on mass differences. So put that in there. I'll put here mass differences. I'll put here heavier ions are deflected less than lighter ones, which makes sense. They're just not going to move as much. Okay. All right, the key to mass spectroscopy is that all the particles go into the deflection chamber with the same kinetic energy. They do not, however, have the same mass to charge ratio. Although most of the ions are +1 ions, their masses are different. Therefore, the amount of deflection they experience by magnet is different. That's like literally what you said for number 5. The strength of the electromagnet can be varied, so only particles with a particular mass charge can make it through the detector. Other particles collide with the metallic sides of the instrument, are neutralized, and then removed by the vacuum, so we can look for specific ones, is what they're saying. The machine is calibrated using carbon-12 isotopes, which are by definition exactly 12 AMU. Consider the following ions formed in a mass spectrometer. Rank the ions in terms of their degree of deflection by the electromagnetic from least to greatest. Greater deflection means a tighter turn towards the magnetic pole or negative pole of the electromagnet. Make sure all group members are able to explain the ranking. So take a minute, pause it, see if you can do this. And what you're going to be looking at is the mass to charge ratio. So for example, for this fluorine, my mass is 19 and my charge is 1. For the oxygen, my mass is 16 and my charge is 1. And for this oxygen, my mass is 17 and my charge is 1. So the one that's going to be the greatest mass to charge ratio is going to be what? It should be my oxygen 16. All right, so O16 I'm going to put here. And then I'm just going to do like this. And then I'm going to put my next one is the O17. And my next one is the F19. I'm not going to put charges on there, but you get the idea. Okay, why is it necessary to have a mass spectrometer chamber under vacuum, very low pressure, for it to work properly? So lots of things can travel through the detector, and if it's not in a vacuum, then it's going to get all kind of gaseous ions that are in the air and contaminants. So that's really the key. So we don't want to change the path of the ions because of other things that are in the air. All right, let me find my second page here. Well, I guess my third page. Okay, so here we're looking at those graphs again, which we saw on our PowerPoint earlier. So Model 2 is the mass spectrum that resulted from experiment in Model 1. What is the mass number of the most common isotope of magnesium? So if you recall, the fact that this first one is highest is going to be the one that's the most abundant. And so we would say the mass number of that guy is 24, right? It's the highest one, so I'd say 24 here. And it says, what is the percent abundance of the most common? To me, if I kind of pull that line over, it looks like it's about 80%. Again, you guys might argue a little different, but it's pretty close. Let me move this so we can see it here. Okay. The average atomic mass of an element can be estimated from data on a mass spectrum. Calculate the average atomic mass of magnesium using the data from Model 2. So remember, we have to do it like that formula we used before. So I'm going to say average atomic mass is equal to, let me move this up so you guys can see it, and I'm going to do 24 times, we just said it was 80%, so I'm going to put 0.80 plus the next one is 25, and it looks like it's about at 10%, so I put 0.10 plus, and then 26 looks like it's at about, it's got to be a little higher than 10, so I'm going to say 12%. So if I multiply all those out, I get 24.82. And that's pretty close to what magnesium is. Magnesium is 24.3, so it's a little off. But again, what it means is my reading of these lines might be a little different than it should be. To be honest, I think they say that it's supposed to be 10, but it does not look like it's the same height as the one for 25. I don't know what you guys think, but I don't think so. So I would accept that. Okay, give 2 reasons why your calculated value in part A is only an estimate of the average atomic mass of the element of magnesium. So one is the isotopes have different atomic masses. And the next one is that these graphs can't be read exactly. That was cannot be read. I'm going to say accurately because it's very hard to tell specifically what the number is. Okay. All right. Table below provides the mass number and percent abundance information of each element of lead. Draw a mass spectrum for lead. So this is literally, they just want you to make a version of this table with these guys right here. So go ahead and pause it, and you would put, and you can make your graph. So you can have mass, charge, like that. You're going to have your percent abundance, and you're just going to label them all out. I would go to 100. And label these. And what does it say? Percent abundance information, okay. And you guys know how to graph, so do I really need to graph this for you? Probably not. Note that we have it. Just remember, I will say this, I will do this part. You should have it like this. We should have a 204 as our lowest, right? And then we have a 206. Sorry, I'm trying to look at it as I go. And then we have a 207 and a 208. So you should have a line for each of those. And I'm not putting percentages here, but you can see. And our biggest one should be the 208, and our lowest one should be the 204. Okay. All right, we're going to continue on with the next page. Give me a second to move things around here. Uh-oh, it might have went through. Okay, so let's take a look at here. So the mass spectra you have been looking at in this activity using percent abundance on the y-axis. Typically, however, the spectra use relative intensity. The ions from the sample are sorted by mass-charge ratio by the mass spectrometer. The ion that hits the detector most often is assigned a relative intensity of 100. Let's just highlight that. Okay, so the ion that hits the detector most often is assigned relative intensity of 100. So now you know that. The other ions are given proportional relative intensities based on their abundance in the sample. An example of magnesium spectra shown above is given in both ways, given below. So it is important to look at what the axis labels are. So the y-axis here is the percent abundance, which we've been used to now. And now they're saying, oh, we can do it another way. We can do it as relative intensity. So you can see they convert the one that's the highest peak to 100 and then kind of figure out these guys, besides that. You're just using a little bit of math here. So it says the sum of all the percent abundances for magnesium is equal to 100. Explain why this is reasonable. Because the percent abundance is equal to all the atoms that went through there. So it should equal 100. The sum of the relative intensities for magnesium does not equal 100. Explain why this is reasonable. We just said what we highlighted up here, because the highest peak, or the highest, or the, sorry, yeah, it is the highest peak, but the highest one is 100. And that's the one that's most often, so they can't add to 100. Does that make sense? Okay. All right, so let's keep going. Imagine that the relative intensities on the spectra read this box represent the number of particles in the sample. Theoretically, how many magnesium ions were depicted by the mass spectrometer? Up. Hold on. I'm going to have to plug my computer in. Let me pause this.